You need to hear this because this is kind of crazy. Earth is the only planet that does that. And why is this happening? So I thought, let's start like this. Hi, everyone. I hope you will like that because it is kind of crazy and highly interesting. Earth, our planet. We have to talk about the crust and all the earthquakes that we're seeing. If you look at the Pacific Ring of Fire right now, all the earthquakes that are happening there, most of the big, strong earthquakes are happening there. We were just dealing with Japan. We had the big earthquakes, Tonga, Indonesia, and stuff like that. So I want to look at why this might be happening, because we have new evidence. What scientists found that is highly interesting for that. They have revealed the earliest evidence for the shifting of Earth's crust. And that really matters because basically the Earth has a rocky crust. It's basically made out of puzzle pieces. And Earth is the only planet that does it like this. That's why we have stuff going on here on Earth that other planets don't. And we talk about that. And I bet you didn't know that. Let me know if you did. So we know our crust is slowly and steadily moving. It's a process that is called plate tectonics. And these dynamic movements helped to do something in the past, but they're also responsible for something that's happening right now. They have helped to create habitats and a climate that has fostered the emergence of life on our planet. But exactly when this geological process first emerged has been a matter of scientific contention for decades, and now scientists say they have found the earliest direct evidence of plate tectonics on Earth, the only known planet to have this geological process. And now you might be surprised. Before we go to the findings, let me explain. So if I want to make that clear a little bit. Is Earth the only planet with tectonic plates moving? No, but Earth is the only planet that we know of with active global plate tectonics like ours. In other words, that means we have tectonic activity, meaning other planets have also tectonic activity. That means their crust is cracking, stretches, compresses, uplifts, or breaks. But they do not show the same full system that our planet has, that Earth has. Large plates that are constantly moving, subducting, spreading at mid-ocean ridges, recycling the crust, right? Especially at the subduction zones where the crust is subducting and then melted, coming up as volcanoes. And that is driving many earthquakes and the volcanoes here on Earth. So on Earth, if we compare it to other planets, active plate tectonics with plates moving a few centimeters or inches per year. Let's compare this to Mars. Mars has giant faults and old volcanic and tectonic features, but no active global plate tectonic system like Earth has today. Mars has Marsquakes, yes, but its crust behaves most likely like one thick shell. What about Venus? Venus has deformation, rifting, volcanism, and crustal blocks, but not clear Earth-style moving plates with subduction zones. Subduction zones are responsible for most of the earthquakes and volcanic areas here on Earth. So some scientists think actually that Venus may have episodic resurfacing or like stagnant lid tectonics. Let's talk about Mercury. It has cliffs and scarps that are caused by the planet cooling and shrinking, but no plate tectonics. The Moon. What about the Moon? The Moon has moonquakes and fault scarps from cooling and tidal stresses, but no moving plates. What about Europa, Jupiter's moon? This is the most interesting comparison of all of them. It has an icy shell. So the icy shell may have plate-like pieces that do move, that spread, and maybe even possibly subduct underneath each other. But that is ice tectonics. That is also different, right? Not rocky plate tectonics like our Earth has. So Earth is the only known planet with an active Earth-style plate tectonics. Other planets, they do have tectonic deformation, but not the full global plate system that Earth has. That makes us unique. And now let's have a look at what they found. So they were looking at, well, when can we say that this process started on Earth? So they think that this phenomenon here on Earth was already shaping our planet billions of years ago. People ask the question, why does Earth have mountains? Why do we have oceans? It only makes sense with plate tectonics. So the leader of the study, Professor Roger Fu, professor of Earth and Planetary Sciences at the Harvard University, was the leader of this new study. And he said, we're trying to understand when it happened on early Earth. That is a fundamental question. It makes everything else make sense. That is how important this is. Today, the Earth has 7 major and 8 minor plates. And on average, these plates are 125 kilometers, that's roughly 80 miles, thick. The crust is thick, and they move. They do move at a steady rate of several centimeters, a few inches per year. Each plate is in motion, either pulling away from each other or growing closer to its neighbors. And then we have the volcanic activity and the earthquakes that typically cluster at these margins, at these borders, at these boundaries. So some in the scientific community contended plate tectonics began roughly 4.4 billion years ago, while others are still saying, well, they only started in the last billions of years. So whether modern plate tectonics directly arose from the hellish magma ocean that once did cover Earth, or whether we have some intermediate stages, such as plates that moved intermittently or one single unbroken plate, it's still unclear. But the latest research reveals the plates were already shifting as early as 3.5 billion years ago. This is called during the Archean Eon, when the planet was already home to early microbiological microbial life. So is that important when we push back the timeline for active tectonic plates? What does it matter? Well, this new study and analysis could offer clues about the early history of Earth and the conditions that supported the early life for us, for our planet. And how can you capture the early history of Earth? Rocks are the clue. So what they have done in this new study, they have analyzed rock samples from East Pilbara Craton. That's a geological formation that is rich with fossil evidence of early organism, such as they're called stromatolites. That's the Western Australia Pilbara region. So they looked at these samples, not a very friendly area. So what the researchers tell us about this area when they were going there, they said, if you don't get too close, it actually looks like a really friendly, beautiful scenery because it's got these like low rolling hills. But once you start walking around, you realize it's full of very spiky grasses with sharp tips. So nature doesn't really want you to walk around there. So for their study, Professor Fu and his colleagues have harnessed a phenomenon that is called Paleomagnetism. So magnetic minerals within rock record the inclination of Earth's magnetic field lines at the moment they form. So it's basically history recorded in these formations, and that allows the scientists to infer the rock's original orientation and latitude. And that is what we want to know. Where did the plates go? How did they move? So a quote from Professor Fu is, he said, "Our job was to basically measure these grains and see what the magnetic alignment of these rocks was. You can take the angle between the observed magnetic field direction and the horizontal angle, and you can say, are you near the poles or are you near the equator?" Interesting, right? So you still are able to detect the location, and they have analyzed quite a few rock samples. They have analyzed 900 that they collected from Pilbara. And the time frame that these samples represented was 30 million years. Isn't that amazing? So what they found out is that part of the formation shifted in latitude from 53 degrees to 77 degrees. This is a drift of tens of centimeters, several inches annually over several million years. And they rotated clockwise by more than 90 degrees. So that is absolutely evident. Then what they were also doing, they were assessing the existing paleomagnetic data from another area in South Africa, from the Barberton Greenstone Belt. This is how this area is called. And they realized that it was nearly stationary at a lower altitude during roughly the same time period. So just by looking at these two different sites, it was clear that the lithosphere of the Earth basically comprises the Earth's crust and the uppermost mantle of the Earth, as you can see in the graphic behind me, was not a huge, big, unbroken shell across the globe. A lot of scientists have argued that it was before. Instead, it was segmented into different pieces that could move with respect to each other. So what they found in this study, guys, that's amazing, and it's highly, highly significant. And if you're interested in volcanoes and earthquakes, this is what you need to know, especially on this channel, right? Let me know in the comments if you agree, because this is so important, because mainly the findings represent a huge amount of high quality paleomagnetic data, and that is uncommon for such old rocks. So again, paleomagnetic data are records of Earth's ancient magnetic field that is preserved in rocks. When we have a volcano, when lava erupts, cools, hardens, tiny magnetic minerals that are inside of it, especially magnetite, they can lock in the direction of Earth's magnetic field at that time. So sediments can also preserve magnetic orientation as the grains settle. So rocks can actually act like a frozen compass of the past. Isn't that amazing? So now, because of that, we can figure out where the tectonic plates used to be, how fast the plates moved, where the landmass rotated, and when the rocks were formed. So the important outcome of this research is the indication of relative motion. This is crucial evidence of how our planet transitioned towards the plate tectonic moving world that it is today. So I hope you liked it. Let me know. Please like and hype this video and check out what else is happening in the world, which is absolutely crazy. Tornado, F4 tornado in the US, and we have same big warnings for the same area and other areas in the US right now until into the next week. Check out this incredible footage here. I see you in a second. Thank you so much.